Okay, so welcome back, and we continue to discuss about the corners. The six. So here's a quick reminder about what we covered so far. And we said corners. So here's a quick review. Mathematically, corners are really simple. They are just functions from binary function on the input space. And then intended meaning of why we are using this kind of binary functions. And the reason is that we want to use this function to measure similarity between two inputs. And what's some of the moral of the entire chapter is that many of the machine learning algorithms can be phrased in terms of similarity measure. If you only know how to measure the similarity between the two inputs, you can train an algorithm and you can use the outcome of the algorithm. So that's one moral of the story. And by the way, the corner is a binary function, and we defined a few conditions on this to make sure this binary function behave like a similarity measure. And the conditions was positive definite and symmetry. And under this condition, we say actually, once we have a positive definite symmetric corners, then we can understand this corner as inner products in a rich feature space. So there is some canonical feature space called reproducing corner Hilbert space, RKHS. So there is a Hilbert space generated by the corner. And there is a map, feature map, that maps inputs to the feature space. Such that, the Hilbert space satisfies many properties, but one of the important bit is that the inner products and the corner operations can be understood as an inner products in that feature space, in the Hilbert space. P prime. Like this. So inner product is, one canonical way of measuring how's the similarity between the two inputs. And this result tells us actually if the kernel satisfies this positive definiteness and symmetry, then the kernel is really computing the inner product in some feature space, which can be infinite dimensional in some sense, in some cases. And then we tried to answer the question about how to build such kernel K. Constructing binary symmetric function is easy, but the tricky part is making sure the positive definiteness. And at the same time, by defining the kernels, what we really want to define, what we want to construct is this feature space, right? Because that we may have a better understanding about what features are really needed to solve some specific problem. So we looked at a few constructions. Those constructions say that if you take the sum of two kernels, products of two kernels, tensor products, and if you take the limits of the kernels, they don't really change. They still give us the PDS kernel. And then we, in particular, by using all these effects, we show that if you take a kernel K and if there's no problem of the convergence issue, if you combine kernels like this, where AN is positive, so it's combining with a power series, this is going to be a kernel as well. And the one specific application, actually there's one more we learned, which is normalizations. And if you combine all of these, we can show that the so-called RBF corners, Gaussian corner is a corner. Which measures x and x prime by taking the exponentiations of their distance, square root distance. Okay, and okay, so then now what we're gonna do today is we will look at one more construction called empirical corner. And then we will look at another big things that we will look at is so-called representative theorem. So which provide a justification or some theoretical basis for using the kernels in an algorithm. Okay, using kernels often means that we are using very rich feature space, which may be sometimes infinite dimensional. So we are using essentially this reproducing kernel Hilbert space, which doesn't have to be finite dimension, doesn't have to have finite dimension, but this representative theorem ensures that sometimes certain optimization problem over this very rich Hilbert space have a very nice form. Which we can express in terms of samples, and that enables us to have an algorithm that works on infinite dimensional space. And the support vector machine is a one instance. Cornerized support vector machine is a one instance of this representative theorem. Okay, so let's go and look at this empirical corner. And later we will ask, so the objective or motivation of the empirical corner is the following. So corners are defined as a binary function. And suppose we have a positive definite symmetric corner. But sometimes we want to have a more explicit representation. So there is a feature phi associated with the corner that maps each input to an element in the reproducing corner Hilbert space. However, but this feature phi may be it's defined mathematically, but may be very difficult to deal with directly. And maybe the feature phi maps each input to an infinite dimensional space. And sometimes we want to have a more explicit representation of a phi. So for instance, we will look at another methodology to achieve this via so-called random Fourier feature and Buckner's theorems later. But in the current part, we will look at the one way of representing phi and having a more explicit approximation of phi. So it's not exactly phi, but we will have some phi prime, and that captures many aspects of the phi and the corner K. Okay. So the situation we are considering is that we have a positive definite symmetric corners, and then we have a feature map phi. Well, actually, it's not really needed. This second part is not really needed, but what we also have is we have a sample, which is sequence of examples, sequence of inputs. So what do we want? So what we want is that we want to have some phi prime that maps each x to an element in this feature space, in the space where the dimension is the same as the number of examples in the sample. such that if we define k prime, x prime as inner products of 3 prime of x, p prime of x prime, then we want that k prime is approximately similar, same as k. In particular, for all ij, so for all the examples in the sample, so sample S, okay. So all the examples in the sample S, we want that these two things becomes almost the same or exactly the same. Okay. Prime same as k, xi and xj. Okay. So what's really going on here? So if you compare phi and the phi prime, maybe phi, as I said, the Hilbert space may be infinite dimensional. So it may, although this is not an exact kind of notation, it's possible that this the Hilbert space is like R to the infinity. Okay. But what we want is we want to represent this phi. Want to have a more kind of easy to handle representations of something easier, some phi version of feature map, which is easier to deal with, like the one that I showed you here. Because it's a finite dimensional, it's much easier to deal with, but we still want it to be quite close to phi in the following sense. If we define corner using k prime with phi prime, that corner behave like a k, especially for all the examples in the sample. Okay, so while we are in doing so, we approximate, so we pay the price, and in return, what we gain is that we have a nice phi prime. Okay, so that's what we're gaining in doing so. So the question becomes how to do so. And then empirical corner provide an answer to this. Oh, sorry. Sorry about this. Okay, so how to do this? So one way to do so is to define, in this k, and this phi prime as a vector, which is constructed by applying k to each between the input x and then all the examples in the sample. This looks like makes sense because the k provide a way, provide a similarity between between two inputs, and one of the success criteria that we have, one of the requirements we have is to ensure, this equality. And then to achieve this equality, what we can do is that we just use the examples in the sample to construct the phi prime. Okay. So that's a one approach. Then we can define k prime of x and x prime as an inner product of these guys. And this k prime is called the empirical corner. Okay. So then we can take a step back and check whether this empirical corner satisfies the property that we aimed at, which is this property. But it turns out that property doesn't hold. So if you compute for similarity between xi and xj using this empirical corner, and that is the same as inner products of v prime xi, v prime xj, and if you just compute the inner products, that's going to be k of xi, xl, then k of xl, xj, where L goes from 1 to m. And now, if you let's look at, try to have some nice form about that tells us what's going on. Let's define so-called corner matrix. So this is a m by m matrix. It's defined defined to be, so each ij entry is just k of I and j. And then with this corner matrix, the property we aim at can be written as, can be written as k of ij, the same as k prime back to xi and xj. So, but now if you write it, what's going on in terms of this, the corner matrix. So then the calculation can be continued, and this is the same as L is equal to 1 to m corner matrix K IL, and then corner matrix K LJ. So that is same as corner matrix square. If you multiply the corner matrix with itself and ij. So we are not exactly what we want. Instead of the k prime applied to xi and xj, same as k of ij, we got k square of I comma j. Okay, and you may just take it just as a fact and then just live with this empirical corner k prime. But you may also ask, the following question: can we somehow modify this empirical corner such a way that our original goal, this one, can be achieved? And it turns out there is a way to do so using the eigen decomposition of K. Okay, so that's what I'll tell you next. So our goal is to define V prime, maybe V double prime now, and K double prime, such that K double prime xi and xj same as K of ij. So that's what we want to achieve. So the question is, how can we do it? And that also provides us, if we want to use empirical corner, so then maybe the K double prime or V double prime that I'm going to present to you is the one that you have to use. So how can you do this? And the idea is to consider eigen decomposition. Of K. So that means we have a orthonormal matrix U. So its columns are eigenvectors of K. And then we have a diagonal matrix sigma, which are the values at the diagonals are eigenvalues, and we have a transpose of U. But because K is a symmetric and positive definite, no, actually symmetric and positive semi-definite, what happens is that the diagonal entries of sigma are all non-negative. So this is just some, the fact that comes from the property that our corner is PDS and the induced, so the induced corner matrix K or ground matrix K have, it's positive, semi-definite and symmetric and have this type of eigen decomposition. Okay, so why we are doing this? If you have this eigen decomposition, so then we can think about, in a sense, square root of the inverse of K. So roughly speaking, we can define square root of K inverse. K may not have an inverse, but we can define something like this using so-called pseudo inverse. So what we are defining here, is this K dagger. We define this one first, which is defined like U sigma dagger, the U transpose. And then sigma dagger is defined like this. It's a diagonal matrix whose ith entry is 0 if the ith entry of the original sigma is 0. Otherwise, so in other case it's positive. In that case, we have a 1 over that entry. Okay, so that's how you define this. And also we can define K dagger in 1/2. Okay. So if you do K dagger 1/2, then it's exactly the same, except that for the middle guy, we take a square root. And sigma dagger half II is 0 if I is 0, otherwise 1 over square root of sigma II. So now if you have this form, then we can now define the new phi double prime. So phi double prime X is defined to be matrix K pseudo inverse, square root of pseudo inverse. Essentially, this guy multiplied to phi prime of X that I showed you in the previous slide. So this phi prime of X, it's just taking the constructing a vector by applying the kernels to all the, to the given inputs with respect to all the examples in the sample. And that's how we defined it. So then we can have a theorem. Never lemma. The lemma said, actually, if we okay, the K double prime is now defined to be sin X prime using inner products using this phi double prime. So if we do so, then it actually satisfies the property that we want. So that the theorem say for ij, if we compute the inner products and the current apply, the compute the similarity using K double prime between xi and xj, that is exactly the same as ij's entry of the corner matrix. Okay, so that's exactly the statements that we are looking for. And the question is, why that is the case? Beforehand, if we just do it naively, we have, instead of the Kij, we have a K square ij. So what really happens here intuitively is because we have this, square root of k minus 1, if you compute the kernel using k double prime, this k minus 1 start to appear, okay? Because this first part will produce square root of k minus 1, the other part will produce the square root of k minus 1. So we will end up with having essentially k minus 1, and that will cancel one of the two k's when we compute the inner products. So that's why we have this ij. And the proof is exactly the one that I told you, but in a more rigorous form. Okay. So they define EI to be, so EI to be the vector which have 1 and 0 everywhere else, but the position of 1 is the ith position. And this is Rn. Okay. Then if you now express this whole thing, so I, xj, you can express this as a matrix operation. So it's a inner products of k dagger of v prime of x and k dagger of and v xi v prime of xj. But using this EI, so we can now express these two guys is a matrix multiplication with a corner matrix K, and in this case it's an EI. We just pick the ith columns of the corner matrix K, and then we are picking the jth column of the corner matrix. So although I don't go to the details of the calculation, if you do the calculation, this is what you can get. And if you just unpack the definition of the inner products, then the inner product is going to be EI transpose, K transpose, K dagger, square root transpose of this guy, and K dagger, square root K and EJ. But what happened is that K is a symmetric matrix. So this K transpose is the same as K. The same K dagger, the half is also a symmetric matrix. This is the same as K dagger half. But what happened is if you combine and multiply K dagger half twice, that's same as K dagger. So what we end up with is that we are multiplying three matrices. One is K. The second is the K dagger. The third is K. But the property of K dagger is if you have, it's not inverse, but it can, in certain contexts, it can cancel K. And this is exactly the context where it can cancel K. So this whole thing becomes the same as EI transpose K and EJ, that is just Kij. So that you can do the proof. So in some sense, what's happening is that after computing the feature map by computing the relationship between the inputs and each of the examples in the sample, we normalize it by computing appropriate inverse, square root of appropriate inverse. Okay. And I don't know, maybe some of you may remember the formula that you will get if you compute the, compute the posterior, or if you use the Gaussian process and compute the posterior distributions, so then the mean formula involves, computing some relationship between the new input and the examples that the new inputs and the examples in the sample, but there's just some normalizing term by like a k, some inverse term. This extra bit correspond to that type of normalization. So if what I just told you doesn't make sense anything to you, it doesn't really matter. So what I meant, the key message that you need to remember is to use empirical corners in a sense properly, you need to put this type of normalization. Okay, so that's the empirical corner. So now let's move to the next topic. So the next topic is normalization. Let's say it's a corner trick. Also, the key, because of the key result is represented theorem. Yeah. So the next part is about, now we learn about kernels. How can you use kernels to design a machine learning algorithm? Or how can we use kernels to generalize existing machine learning algorithms? So let's start with this generalization. Okay. We learn about support vector machine. For the non-separable case, then there was a primer form of support vector machine and also dual form of support vector machine. Okay. And both of them involve solving some optimization problem. And then the solution of the optimization, from the solution of the optimization problem, we can extract the hypothesis or classifier for both problems. For the classification problem. And now let me write this dual formula. Dual formalization. Dual formalization solve the following optimization problem. Try to find the screamum of alpha, where it maximize the sum of alphas minus some quadratic term. Ij to m phi for j. Yj. And subject to some condition. And then the condition say each of these alpha i's should be between range 0 and some constant c. This is coming from the the term that balance between or in the primer form, the size of the weight or the slopes, and some empirical errors that comes from the slack variable. But anyhow, there's just some constant c. Then the other condition is that if you just add all alpha I with multiply with y, it has to be equal to 0. So that's what we learned before. Okay. And then we said, once we solve this optimization problem, so this optimization problem has a maximum because it's bounded and continuous. And then once we solve this optimization problem, then if we can find some I0 such that we have this corresponding alpha I is between 0 and c, then the classifier that we can learn from here is of the form. So our hypothesis will be the form. So sine of the sum to m phi, just write a star yi sine x plus yi0 minus m alpha I star yi, xi, and xi0. So that's the in a sense outcome of solving this optimization corresponds to training or learning. This H hypothesis is the outcome of the learning. But now if you take a step back and look at what's really going on here, both of these things, only use informations whenever it uses information about the input, either in the sample or in the training set, or inputs that coming from for which we want to make a prediction. We are only using inner products. Okay, so if you look at it, then we are only using inner product there and inner product here. So what this does that suggest is that we can actually change or generalize this algorithm by replacing this inner product by a kernel. So if you use a kernel K, so then using the kernels, we can replace the first guy by kernel applied to xi and xj. And this one can also be replaced by kernels xi and x. And this one also can be replaced by kernel k, xi, and xi0. So what does this mean? This means that, if you forget about how these things are derived, if you only focus on what my algorithm is doing, and just replacing the inner product by the kernels, the training can be done with using the kernels, because kernel includes inner products. It's a kind of generalization of the training, and the outcome of the training can also be generalized in the same way, so that we can use the kernels there instead of the inner product. So entire algorithm can be generalized. Okay, so that's something called the kernel trick. So several machine learning algorithms, when we take a step back and look at what's really going on, they are using informations about the inputs only via inner products. So then by replacing this inner product by any kernels, then we can generalize this algorithm. And in particular, in doing so, the original, even though when original algorithm is designed for computing, say some hyperplane, some linear classifier, if you kernelize it, then you end up with the same algorithm that working on the nonlinear classifier. So you can generate the power of the algorithm dramatically. Okay, so that's something called the kernel trick. But you may take a step back and think about, okay, what's really going on here? I just explained the kernel trick of kernelization. From purely methodological perspective, just take an existing algorithm, replace all the inner product by the application of the kernels, so that it gives a new algorithm. But the original algorithm is derived based on some principle. So then can we say something similar for this new algorithm derived with the kernel? And the answer is yes. So then any principles? Or rational, maybe the better word is rationale. And the answer is yes. So what really happens is that if you kernelize, we are really changing the feature space. You can say input space or feature space. So instead of designing an algorithm on the original input space X or original feature space X, we are using reproducing kernel hyperspace, which is typically a much richer space than the input space X. So in some sense, if you do this kernel trick, what really happens is that we are essentially doing the same thing as what we learned for the support vector machine, but the only change is instead of using the original input space X, we are really using much richer space, which is called the reproducing kernel Hilbert space. Okay, and then all the inputs, instead of thinking about input X, which lives in the original space, like an example in the sample, we are using their embeddings into this Hilbert space, well, the feature encoding of these inputs in the features in the Hilbert space via this feature map associated with the kernel. But then after this encoding, all the rest is the same. The optimizations, like support vector machine, is that it's a optimization based on maximizing the margin, and we are doing the same thing. It's just that instead of we are using much richer space in this case here. Okay, and right, and then if we follow that, if we apply all the derivation that we have done using this richer Hilbert space H, then we will get exactly the algorithms that we obtained by this kernelization. So although it looks like just a simple algorithmic or methodological trick, what really happened there is just some rationale or principle behind it, which is instead of using some original feature space, use much richer features, much richer feature space, which may be infinite dimensional. Okay, so that's what's happening. But now you may then take maybe ask further. Now then you may kind of think, okay, so this is a bit like we are originally designing an algorithm on X, and then we are, in a sense, it's replacing X by H. But you may think about designing an algorithm directly on H. Okay. So suppose you design an ML algorithm, which means that training is done. I mean, it specifies how to do the training, and also it tells us how we can use the outcome of the training to solve some specific prediction problem, like a classification problem or regression problem. So that suppose we designed an algorithm. So this is a quad algorithm because we just designed some method using space H. But so we want to use this algorithm. We want to really remove these quads here and then make it really an algorithm. But we might be in trouble because this is space H. And we are thinking that we used here, maybe infinite dimensional. So then, I mean, we cannot even represent each input in this Hilbert space, okay? And typically, machine learning algorithms are expressed in terms of optimization. Its training is expressed in terms of optimization. And then the outcome of the training will return something. But this designing the machine learning algorithm over H means that we have formulated some optimization problem over H. But because this H is a very rich space, maybe solving this optimization may be impossible because the solutions can be like if it's a reproducing kernel Hilbert space, it can be some arbitrary function. There's a function it can be some functions, and then maybe it's very difficult to solve this optimization problem. It turns out for certain this idealized machine learning algorithm using H, more specifically certain optimization problem over this reproducing kernel Hilbert space. So actually, so reproducing kernel Hilbert space, sometimes those are the certain optimization problem have a very nice representation that enables us to design an algorithm. The real algorithm, not just this hypothetical idealized algorithm. So what is the one that enables us to do it? By the way, some simplified version of support vector machine is also an instance of what I'm going to tell you now. Okay. And then this type of magic, which converts optimization over H into the realistic algorithm, is the theorem. So in the textbook, it's written Theorem 6.11. So the theorem says the following. So it says that we have, so the user's setup, we have PDS corner. And we also have a reproducing corner Hilbert space. And then feature map for they are RKHS, also feature map of K. And then we are assuming some optimization problem. Then we assume that optimization problem have two components. So the optimization is F is an optimization objective, but this optimization that we are trying to solve is over RKHS. So you take some elements, which is a function in the, that take input X and return the real number. So this F is an optimization objective, but then F is defined in this way. F of H, B, G of So G corresponds to the regularizer. We say that we compute the size of H, and then we map it to, that's going to be a number, and then we map it to a number. But G corresponds to the regularizer. And then the other part is something called loss that corresponds to the loss with respect to the example in the sample. So we compute x1, L of xm, and then compute the loss. So the L has an information about y1 up to ym inside. It's all built in. And then so it's a, if you give the value h of x1 up to h of xm, it tells us how good our the classifier h is with respect to the examples x1, y1 to xm, ym. So this corresponds to the loss, the empirical loss, and this corresponds to the regularizer. And formally, the condition is G is non-decreasing. What this means is that if the input, the H is larger, then the G maps it to the larger value typically. It may just return the same value, but it never returns something smaller. Okay? So regularizer, in a sense, encourages the small h. So that's our optimization objective, and then we assume that computing minimum of f of h has a solution in this reproducing corner space. So really, we are thinking about optimization problem on the Hilbert space H, which have this regularizer part, and then we have this empirical error part together. And we are assuming that that optimization problem has a solution. I mean, some optimization problem doesn't have a solution, but here we are assuming it has a solution. If that is the case, then the theorem say that actually the solution should have the particular form. So, I mean, no, there is also solution H prime, which may be different from the solution above, such that H prime is of this form. So H prime is a map because it's a reproducing counter space is space of functions. But then it's this H, it can be any with like some very kind of any function in H, okay? But this theorem say that actually, if there is a solution, then we can always find a solution of a very nice form, which can be expressed in terms of examples. Some examples like this. So this means that when you search for a solution of this optimization problem, instead of searching over the entire Hilbert space H, which is extremely large, we can search over functions in this RKHS, which have this particular form. It's a linear combination of the functions in RKHS that's obtained by the applying K to one of the examples xi. Okay. So we have the x1 of the xm. Then it becomes the finite dimensional optimization problem. All we need to find is beta, the finite dimensional optimization problem. So we can solve this, most of the time. Okay. So that represented theorem say, in theory, we have a very rich space, but if the optimization is formulated as a regularizer plus the empirical error over the examples in the samples, so then whenever there is a solution, we can always find the solution of some nice form or some simple form. And then furthermore, there's so if G is strictly increasing, then all solutions have the above form. So the above form, this guy. Okay. So that's the presented theorem. So now the question is how we can prove this theorem. So the proof is actually quite easy. So I will only show the first part, the existence of H prime. Then suppose we have a solution. So H is the solution of this optimization problem. So then we think about a subspace. So we define H1, which is a subspace of H. As all the functions in H that can be expressed have this form. Okay. So formally what that means is it's a span all the linear combinations of functions xi where I is m. So anything that's obtained by embedding examples in the sample, any linear combination, that's going to be our space H1. So that's also, I mean, the subspace, the inner product space of H. So that's we are defining some subspace. It's a bit like this. I mean, although this is not a perfect analogy, one good analogy is think about this H as a maybe three-dimensional space. We are really taking some hyperplane there. So we are taking some two-dimensional space H1. Okay. So we have three-dimensional space. We are taking the plane there, which is a two-dimensional space. If we do so, then I mean we can for any H including this guy, we can decompose H into two components. One is a component that belongs to this subspace H1. The other is a component that is orthogonal to the subspace H1. And there exists H1 in H and H1 H1 perp such that first H is decomposed with H1 plus H1 perp, and H1 perp, the second guy, is orthogonal to any element in H1. So the Hilbert space for H. We pick this subspace, any element in the subspace, and if you take inner products, that is going to be 0. So it's really, I mean, I think maybe plane. So think about this H as a three-dimensional space, and this is a plane determined by xy. So really, this H1 is a projection to xy. This perp corresponds to the projection to the z axis. Okay, so just z coordinate. But that's what we get here. So then that we claim that H1. So H1 is so there's H1. This small H1 lives in this Hilbert space H1, no, Hilbert space, the subspace H1, and that's a span. So H1 should be the form that we claim in the theorem. Okay. It looks a bit messy. H1 is exactly of that form. So all we need to show is that for what we need to show. So need to show that the f of H1 is smaller than equal to f of H. That's what we need to show. Okay, so that implies H1 is also a solution of the optimization problem. So why that is the case? And but by Pythagoras theorem, we know that this size of H is equal to, in this space, is the same as size of one component and its orthogonal complement. So this is essentially a Pythagoras theorem. So, and then every norms are greater than equal to 0. So we have, I will ignore, I want to write the subscript H. H1, norm of H1 is smaller than equal to norm of H. So if you apply G, because G is non-decreasing, G of H1 smaller than equal to G of H. And then for the other, so this shows that as far as regularizer is concerned, H1 is as good as H. Okay. Now for the empirical error, we can use a reproducing property. So one property we can say is for every 4xi, okay, 4I in n. Now think about the h of xi. If h of xi is same as h1 of xi, then we are done because the loss that we are using there, I mean, the other part that we have to worry about, the loss is only using informations about how h behave with respect to x1 up to xm. H and h1 behave exactly the same for all those inputs. Then, I mean, we will get exactly the same loss. And so, but it turns out that is the case because of the reproducing property. And this is the same as H and the corner K, the inner products. Now, if you look at this H, I mean, H is the same as H1 plus H1 perp. So we have this. So we plug in this H1 plus H1 perp, and then we use the linearity of the inner products. Then we get H1 K of xi plus H. Let me extend it a little bit more. H1 perp K of xi blank. Okay, the first part is same as H1 of xi because of the reproducing property. Reproducing properties say function application is the same as inner product. But the second part turned out to be 0. So that's why two things are the same. And why is 0? And this is 0 because this is a 0. And the reason it's a 0 is because of this property. For any H1 prime in the subspace, its inner products with H1 prime is equal to 0. But this K, xi, comma blank, this is exactly one of the elements that is in H1. Okay, so their inner product has to be 0. So this means, so we have just shown, as far as inputs xi is concerned, H and H1 behave the same. So that shows, I mean, that for the loss, the H and H1, the empirical loss, they will produce the same value. So that's why we have this inequality. And that implies H1 is also an optimal solution. And then if G is strictly increasing, then we can also show that all solutions should actually have this form. Okay. But where we are, so the representative theorem say, if we have an optimization problem formulated over the reproducing kernel Hilbert space, but if optimization problem is kind of typical form that we have been studying so far, regularizer, objective optimization problem has a typical form that we have studied so far, regularizer in terms of size, plus the loss, empirical loss in terms of examples in the sample. So then, and whenever that optimization problem has a solution in this rich space, it also has a solution in a much more restricted space expressed in terms of examples. Okay. And this representation tells us instead of searching over the big space H, we can search over some much smaller space and get a solution. Right. So then, as I said, the support vector machine, although I'm not explaining and spelling out all the details, is actually, so what's going on in support vector machine can be understood as the application of this representative. Now, in the remaining 10 minutes, let me mention the last bits in the textbook, which is about the so then, which is about the analysis of this learning algorithm, okay, especially support vector machine. Can this also be generalized? So we we learned about so-called margin theory. They provide a justification about the support vector machine algorithm. The margin theory say, provide an upper bound of risk or generalization error in terms of so-called margin empirical error plus some term, but that upper bound give instead of just giving a Rademacher complexity and empirical risk, it had some extra parameter that's called the margin parameter. By changing the margin parameter, then this upper bound can be made much tighter. Okay. So one of the results in the margin theory. So that's the margin theory. We learned about the key theorems that we studied is something called the Theorem 5.8 and Theorem 5.9. The message is that all these results carry over to normalized SVMs. And actually, so in some case you can have make this bound a bit tighter. So let me just show you this theorem, how this theorem 5.8 can be generalized here. But theorem 5.8, theorem 5.8, well, it can be exploited and derive something for the kernelized support vector machine. Theorem 5.8 says the following. So it talks about two things, but let me just mention one thing only. It says that if we have some so we went to space F, X, and I think I wrote it like this. So we have some probability distribution on X. And we have a margin rho. And our hypothesis set is defined as map such that norm is bounded by lambda. And furthermore, if whenever we sample the probability, so all the samples are bounded. The x component of the samples are bounded. So if xy sample from D, size of x is bounded by R with the probability 1. If that is the case, we have some delta which controlled what we want to achieve, and m is the number of samples, number of examples in the sample. So then we have to say the following. For m samples, we have this uniform bound. For every f in f, its risk of the hypothesis that's obtained by composing with the sign is bounded above by margin risk, empirical margin risk of f plus rho over 2 and the Rademacher complexity over the hypothesis set and 2m rho over delta. So that was the form that we studied before. And then this one, we said it's interesting. That's because there is a rho parameter. If row parameter is large, then this second component will become small. But on the other hand, the first component, which corresponds to the empirical error part, will become large, and the vice versa. If small row, empirical error part will become large, but the Rademacher complexity part will become empirical error part will become small, Rademacher complexity part will become large. So there is a trade-off, and then this bound help us to understand the trade-off by using the different margin, which is happening in the mixed margin classifier algorithms like support vector machine. Now it turns out this type of theorem can be generalized for in the setting of a corner-like support vector machine. So that is theorem, well, I think it's a corollary 6.13. So in the generalization, which part is changing? The first thing we change is that instead of using this inner products here, we are really thinking about the inner products in the reproducing corner Hilbert space. So we are having corner K. So the red part is something added. This is a PDS corner. And we are also thinking about its reproducing corner Hilbert space. And its feature map V. So the usual suspects from the K. And then what we do is that we are thinking about now weights, not in the reproducing corner Hilbert space. So X instead of X, we use its feature in the RKHS, and the inner product is taken in this Hilbert space. The weights is bounded in this Hilbert space. Okay. And also for the input, we are thinking about this input not in the original space, but we are thinking about this size in the Hilbert space is bounded by R. And if you do so, the theorem just holds. I mean, actually the same, the theorem, it can be instantiated in the setting because it works on any Hilbert space. But the interesting bit is that now, when in the chapter 5, what we did is we replaced this Rademacher complexity to something that is manageable, and same kind of replacement also works in the in our corneralized version. So the red part is the change, and then this part will also be replaced by square root of square gamma square in M, and this is done by the theorem 6.12. So I mean, maybe it looks complicated, but what's happening is that essentially most of the results that we already have for the support vector machine can carry over to the kernelized support vector machine. Just before finishing, let me mention one more thing. Now, suppose we have our kernel K is normalized, which means that the K of XX is either 0 or 1. I mean, we learn about the normalization construction, so we suppose the K is obtained by applying it. So the one example is the RBF kernel. So if that is the case, then the size of this guy is going to be at most 1, okay? Because I mean it's the K applied to XX and square root of K applied to X, I mean X comma X, and that is either 0 or 1, so it's bounded by 1. So in that case, we can simplify things further. So the R part that appears here, it can be replaced by 1. Not much, but we can also do the simplification. And then this makes sense because, I mean, when we know the instance, which is RBF, which is used quite often in practice. Okay, so that's it for today, and to see you again on Thursday. So I'm gonna be here for about 5 more minutes. So if you have any questions, you can ask me. Okay, so thank you very much.